All right, so we'll get started with a couple reminders. Homework due tonight, okay? So still before midnight. Make sure you take some time to finish them, the problems. And then exam one is next week, okay? And then for in-seat classroom surface disinfection, Cassandra and Olivia, okay? Um, so for the exam next week, it's going to cover chapter 1 through 3, okay? So the most important part is the one-dimensional and two-dimensional motions, okay? So make sure the study guide for you guys is to make sure you can solve the homework problems all by yourself, not looking at the solutions, okay? So make sure you can solve them, and you should be ready to go for the exam, all right? If you feel like if you are not quite good at solving certain problems out of homework problems, then you probably want to take a few more exercise. Just pick like a couple exercise from the textbook, okay? At the back of textbook, and then do additional some practices, then you'll get used to it, okay? But make sure you can solve the homework problems all by yourself, okay? All right, so today we'll probably be looking at chapter 4, okay? But before we do that, we still have some remaining business in chapter 3, okay? So last time we were looking at the part A of this problem, and archer shoots an arrow at the 75 meters distant target. The bull's eye of the target is at the same height as the release height of the arrow. And then it asks what angle the arrow must be released to hit the bullseye. So we saw for that one last time, okay? We look at a couple different methods last time. So one is to solve for t first, and then let me see. Oh, we actually look at the two equations, x direction and y direction, at a simultaneous time, and then we solve two equations for two unknowns. That's what we did last time. So we solve for t and then theta. Okay, so I think what we just need theta, so we just solve for theta. We didn't solve for t. And then the second method we used last time was to just use the range equation from what we learned earlier, because the arrow starts at one level and then hits the target at the same level. So then you can use the range equation, which is much more simpler to solve. Okay, that's what we checked earlier last time. Now this time we are going to check B. It's asking you if there's a large tree halfway between the archer and the target with an overhanging horizontal branch 3.5 meters above the release height of the arrow. Will the arrow go over or under the branch? Okay, so let's take a look on this. All right, so I'm going to just borrow the figure that we had last time here. Okay, so last time this is the figure or the sketch I drew. So this initial speed 35, this angle we saw it to be 18.4. Okay, so now this becomes a known of 18.4 degrees for the angle. Okay, if yeah, let's just take that. For this guy here, it's asking you if there's a branch, a large tree in between. Okay, so I'm going to draw a tree here with a horizontal branch over here. Okay, somewhere here. So this is the height of this branch is 3.5 meters. Okay, so that means the y position of this guy, or the y position of the branch, okay, is 3.5. Okay, Now you want to know if your arrow goes above or under the branch, okay? So that means you need to figure out what's the y position of your arrow when it's at the halfway of the flight, right? So that means you're looking for your y of your arrow, right? So if you solve for your y of your arrow in between here, in the middle way here somewhere, okay, the branch here. So this is the middle way where the x is equal to 1/2 of the 75 meters, right? So in midway, so that tells you your x position here. Now you're looking for y. Okay, so that's basically the problem is, okay, it's asking you to look for y and then compare your y with the 3.5, right? If your y is greater than 3.5, then the arrow goes above the branch. If the y is less than 3.5, then the arrow goes below the branch, okay? So that's the problem here. Now let's take a look. How do we want to solve for y? So we're probably looking at this equation of motions in x and y directions, right? So for this again, these equations again, all right? You are given x equal to half of 75, then you're looking for y. So you can see, as I mentioned in last class, so most of the quantities here in x are different from the quantities in y, except the t is the common factor, right? So if you are given x, then you probably would like to use that information to solve for your t in the equation of motions in x direction. And then you can take the t in the equation of motion in the y direction to figure out your y, okay? So that's how you wanted to tackle this problem here. Given x here, then this x, okay, is the half of 75. All right, this is the original position. We take that as the origin. Okay, so let's do it this way. We are going to look at the first equation because that one has x, okay? The next two, they are pretty much the same without x, okay? So then you're going to set up this x equals to x naught plus v0 x times t to see if you can figure out t, okay? So this guy is 0. This guy is the 1/2 of 75. Then equals to this times t, right? So you only need to know what's your v0 x, the velocity x component, okay? Initial velocity x component. So v0 x should be equal to v0 cosine of the theta, okay? Let's see if we have v0. Yes, that's given 35. And then do we have the theta here? We did figure this out, right? So in part A, so then we will take that as our theta here. So you can plug in your numbers and then figure out this number, okay? But I'm going to just write this here, the v0 cosine in the place of v0 x, okay? So this is equal to v0 cosine theta, okay, times t. So then my t should be equal to 1/2 of 75 over the v0 times cosine theta, the 35.0 meters per second times cosine of 18.4 degrees, okay? So then I can solve for my t. Put it up. So it gives you 1.129 roughly. That's the time it takes to reach the halfway of the flight, okay? So then once you have that t, you can take t into this equation. I think that will give you the y that you are looking for, okay? So the y halfway. So then y equals to y0 plus v0y times t minus 1/2 gt squared, okay? You know everything on the right, then you can solve for your y, okay? So the first one is 0, so we can leave that out. So this guy will be v0, again, v0 sine theta. Did we have that number last time? I guess we didn't, but we can plug in the numbers into the equation here, okay, times t minus 1/2 gt square, okay, so then 35.0 meters per second sine of the 18.4 degrees, okay, and then times the time of 1.129 second minus 1/2 9.80 meters per second squared times 1.129 seconds squared, okay? With all these numbers in your calculator, it tells you this is about 6.247 meters, okay? So compare this number to the 3.5, you are greater than the 3.5 meters, right? So you will go above the branch, okay? All right, so that's what we didn't finish last time. Right, there's yeah, so the question for online folks, the question from class is there a way that to figure out the height because it's halfway? I think we talked about that a couple of times earlier. So because this happens at exactly at halfway, okay, so you can figure that out another way, like just because you are halfway, so you probably know that the arrow in vertical direction will turn direction. So you can probably use this equation. The Vy at that point will be 0, right? Because it turns directions. And then this guy, you can figure it out, okay? By given the initial magnitude of the velocity and then the directional angle. So the y0 is 0. So you can use that equation, okay, to figure that out directly without figuring out the time t, okay? This happens exactly at halfway. But in general, sometimes when the problem might be asking you just in general a position, not halfway, okay? So then you probably want to follow this procedures here. So solve for the time t first, and then take time t in the one of the equation of motion in y direction to figure out your y, okay? So yeah, both ways. This is a particular one that is halfway. You probably have another way of figuring it out, okay? So take that one. You probably can do it that way. Yeah, I think you can do it that way. Mm-hmm. And as you mentioned, because for hardware, that I think one of the example we look at, we figure out an expression for the t would be just that is to figure out t in another way. Okay, so t is equal to v0 y initial divided by g. Okay, at halfway, that's what you could have. Okay, now you can take that time t into this equation again. Okay, so either way, you should be able to figure it out. Okay. All right. And I believe in at least one of the homework problems where you are given either y and then looking for x, or the other way around, given x and looking for y, okay? So then this is the steps you want to follow. You want to take advantage of the given either x or y, solve for t, and then take t to the other dimension to figure out the distance in the other dimension, okay? All right, other questions anyone else might have on this one? Okay. So if not, then we are going to look at chapter 4. Okay, so again, the exam one will only cover chapter 1 through 3, but because we have a lot of content to cover, so we'll just continue lecturing here. Okay. All right. So in chapter 4, so the previous chapters 1 and 2 and 3 we talk about motions, okay? We didn't talk about what's the cause of motion, so what causes an object to move at the initial place, okay? So it's basically that force will cause an object to move, right? Because if you give an object a force, then it's going to move in the direction it's the force is applied, okay? So then in this chapter, or starting from this chapter, we are looking at that, okay? What causes the object to move. So for force, I think we haven't defined it officially, but it's quite intuitively. So it's either you are giving an object a push or a pull, okay? So if you push the object, then you are giving a force. If you are pull it, you also give it a force, okay? Looking at the figure here, if you go ice skating with your friends, if you give your friend a push, then you will see your friend will start moving, right? So in this case, either you are pushing or pushing or pulling, then you are also giving a direction, right? So that means a force is a vector, so it has magnitude and has direction. So if this friend is being pushed by two other friends, then she will receive two forces, okay? So then coming from these two forces, you can figure out what's the total force or the resultant force, okay? So this week's lab is dealing with that, okay? So for you guys in Wednesday section, you already see how you can do two forces add up, okay? And then the rest of you guys will do this this afternoon on this one, okay? So it's a vector addition here, all right? Now for vector addition here, because you are adding two forces together, okay? So F1 plus F2, then the resultant will be this guy, okay? So you can see F1 and F2, and then the resultant will form a triangle, okay? So then if that's the case, you can use law of sines or cosines, okay, to figure out the magnitude of the resultant and also the direction of it, okay? So that's one of the ways you can do vector addition, okay? But let's look at this triangle over here. In general, when you have two forces adding up, then you should form a triangle with the original two vectors and then the resultant vector, okay? So then with that, let's take a look on if you have two forces, their magnitudes are F1 and F2. So what would be these two adding up together, which of the following statement about the net force is correct, or the resultant force is correct, okay? So think about you have two forces add up, and then with the resultant, you will form a triangle among those three. What will be the magnitude of the net force? Okay. And tell me what you think by clicking on the problem here. Then you can submit your answer. All right. So we can take a look here. So assuming you have F1, you have F2, okay? Now, this is what you can form, right? So then you have a triangle among those three sides here, okay? So you can see for F1, F2, F1 plus F2, okay? This is one of the scenarios, right? You can also have, say, F1 here, and then you have F2 right on top of it, if they are pointing in the same direction, right? So in this case, then F net is equal to F1 plus F2, right? Without an arrow, that means we are talking about the magnitude, okay? So then in this scenario, this is equal to that, those add up, okay? In this scenario, you can see then F net is going to less than this plus that, right? Because in a triangle, any side should be less than the other two sides add up, right? In a triangle, if that's the case. So then F2 or F net has to be less than F1 plus F2 in that case, okay? And then it should be greater than the subtraction of one side from the other. So if you are doing it either way, depending on which one is larger, okay? But let's take a magnitude of the absolute value of these two, okay? So in the scenario, if it forms a triangle, or in a scenario that if F1 is in this direction, F2 is in right in the opposite direction of it. So F2 goes in that direction. So then your net force will be just this guy, right? That will be your net force. So in that case, then net force is equal to F1 minus F2. Okay, again, just because in this figure here, F1 is greater than F2 doesn't guarantee that F2 is always smaller than F1. Okay, so to be safe, you can always take a absolute value of that. Okay. So you can see among these three different scenarios, I think out of these three scenarios, we cover all the possible scenarios that we could have. Okay, so F1, F2 could be in the same direction, could be in the opposite direction, or in general, they form a certain angle. Okay, then you will have a triangle like that. Okay, so you can see then to summarize, so this one for the net force, okay, the lower limit is going to be this guy. This is a larger limit, okay, and then anything in between is here. So then you should expect F1 minus F2 to be less or equal to the F net, or less or equal to the two add up, okay? So this is what you have for the two vector addition, okay? So then back to the original options we have. Let me pause for a few seconds for you guys to take notes down. So keep in mind, because when you are doing vector additions or the forces adding up, you're actually doing vector additions, okay? So then you cannot simply just add the magnitude up, okay? It depends on the directions of the two mix, okay? All right, let's go back to the slides. So then looking at the options, A says the net force must have a magnitude equal to F1 plus F2. Okay, it could, okay, but not must. Okay, in general, it shouldn't be equal to that. Okay, and then B says the net force can have a magnitude less than F1 plus F2. Okay, so that one is correct. So B is correct because most of the time it can be less than the magnitude of the F1 and F2 add up. Okay, C says the net force can have magnitude greater than F1 plus F2. That's not possible. Okay, you cannot have magnitude net force having magnitude greater than the original two add up. The net force has a magnitude greater than F1. Okay, so D, it could be, right, but you shouldn't say has a magnitude. Okay, so that means must. Okay, so it could be greater. That's the more accurate way of saying it. Okay, could be greater than F1. All right. All right. So the correct answer for this one is B. Okay. I think some of you guys got this right. Okay. But not all. A couple of you guys got this one right. All right. Any questions you guys might have? Okay. So as we mentioned earlier, if you apply force to the object, then the object starts going to be under the influence of this added force, okay? So then a lot of times when you have multiple forces acting on the object, so then you wanted to illustrate all the forces, okay, that is acting on the object, okay, to give you an idea how the resultant force will be, okay? So if you are drawing all the external forces acting on an object, then if you are doing that, so then this is called doing a free body diagram, okay? And then this technique is very helpful when you are solving for a problem if there's force acting on the object, okay? Now, be careful about the wording here. It says external forces, okay? So that implies in some scenarios you might have internal forces, okay? So then you don't want internal forces on the free body diagram. You just need the external forces, okay? So for example, if you have a system that is moving, that has multiple objects inside it, okay? So then between the objects, they might have interactions with each other. Those are called internal forces, okay? But if you just have a single body, then you will not have internal forces, okay? All right. So for a system of multiple objects, when you are considering the system as a whole, then you'll ignore the internal forces, okay? But if you'll be just looking at one of the object inside the system, then you'll be looking at all the forces on the object, okay? So then in that case, don't get confused with the internal forces and external forces, okay? Because if you are looking on just one single object, then every forces on it will be external forces, okay? I think we are going to get into details more later on, okay? But so for the free body diagram, okay? So here are a few steps you want to take, okay? To draw your free body diagram. So you want to sketch the forces, okay? So So I would suggest you sketch them according to scale. So say if you have 2 newtons force versus a 5 newtons force, okay, do not draw them as the same length. Okay, you probably want to have like proper scale, roughly like 2 will be a shorter one, and then 5 will be roughly 2.5 times of that. Okay. You also want to identify the object of your interest. So as I mentioned, sometimes when you have a system of that is having multiple objects, then you want to isolate which one is your object of interest. Okay. Choose a convenient coordinate system. Okay, so XY system, because then if you have multiple forces on the object, then a lot of times you'll be doing forces adding up. That means vector addition, right? So since the forces are most commonly, they are 2-dimensional, so it's important to have a XY coordinate system there. All right. So once you have that, then you can resolve your forces into like components. Okay, so if you are doing vector addition, then you can do the component method. So figure out the X and Y components and then add them up. Okay. All right. And at the last step here will be applying second law to each coordinate direction. Okay. So that means in many cases you will have 2-dimensional motions, or maybe I think we are just going to deal with 2-dimensional motion in this class. Okay. Some scenarios you will be doing like 3-dimensional motion, but not in this class. Okay, maybe somewhere else. So then you will apply Newton's second law to each coordinate direction. We'll mention about Newton's second law just later in this chapter, a little bit later. Okay, if not today, then next time. All right. So this is the a free body diagram, one example of what we saw earlier when a friend is out skating and then 2 other friends are pushing on her. Okay, so you have F1 and F2. Okay, so if you're looking at her body here, figuring out the motion of the body here, then this is the object of interest. Okay, so to represent the object of interest, you don't have to draw a fancy picture like this. You can just use a dot, okay, to represent your object of interest. So then this scenario can be represented by a free body like this. So the dot is the body of the person. Then there's 2 forces on the body here. So one go to the right, one goes upward. Okay, so then these are the 2 external forces on the body. Okay, that's the free body diagram of the person. We'll be looking at a couple more examples here. So for example, if you are holding a book here, then looking at the book, if you are wondering what's the free body diagram on the book, okay, so then you isolate the object, okay, so then just look at the book, and then you can represent the book by just a dot, okay, and you can figure out that there's probably 2 forces on the book, okay, your supporting force by your hand, the supporting force by your hand, F, which is holding this book in the upward direction, it's acting on that in that direction, okay, and then there's weight of the book, okay, pulling it down. So these 2 should balance out. So then the book is resting on your hand here, okay. So this is the free body diagram, and then you also want to specify what's your X and Y direction in this case, okay. So X to be in the horizontal, Y to be the vertical upward, okay. So then the dot with the 2 forces, it's the free body diagram of the book, okay. You can see these 2 forces are about the same length, but in opposite direction, okay. So that's how they balance out. All right. So that's on the force and free body diagram. That's the first section. The next section here in the book talks about Newton's first law of motion. Okay, so you probably heard about Newton's laws of motion. So there's a few laws. Okay, first law, second law, and third law, and then there's Newton's gravitational law, universal gravitational law. Okay, so that's a fourth one. But in this chapter, we'll be just looking at the first three. Okay, so the first law, it's often also called the law of inertia. So the statement of it says an object continues in a state of rest or in a state of motion at a constant speed along a straight line unless compelled to change, let's say by a net force. Okay, so simply put it into another word, that means if there's a net force on the object, then the object will be changing. Okay, the velocity will be changing. Okay, so when it has a state of rest, so that simply means its velocity is zero. Okay, when it has a constant speed along a straight line, so that means velocity is constant. Okay, so if velocity stays at zero, we can also say velocity is constant, right? It's constantly zero, or it's constantly with certain number. Okay, so so then this is the another statement, which I think is better description or easier, shorter one. It says unless there's a net force, the velocity will not change. Okay. If it's at rest, it remains at rest. If it's moving with a constant velocity, it remains with that constant velocity. Okay. It's also called law of inertia, or yeah, I think it gets the word by saying the object is lazy. If there's no force, external force on it, it will not move. Just like us, right? We are lazy if we are not forced to do something, right? Yeah. Now, why the object is being lazy? That is because it has certain mass. Okay. So the mass is the measurement of how hard it is to change an object velocity or inertia, or you can say it's how lazy is the object is. Okay, if it's a bigger one, then it's harder to make it move. Okay, and then it's also a measure of the quantity of matter in object. Okay, so in chemistry, mass is like probably equivalent to like how many atoms you have in a substance. Okay, so you can calculate that way. Mass has a SI unit of kilograms. Okay, not grams. So this guy. Okay, remember this is kilogram for the SI unit, not grams. In the table on the right here, it lists some of the typical masses measured in kilograms. Okay, so the Earth is a very big one, roughly 6 times 10 to the 24 kilograms. Okay, and then our human body is like about 70 kilograms, or maybe a range of from whatever, like from 50 to 100, or in that range. But probably this is the average number there. A car, automobile is roughly like a ton, or more than a ton, like 1200 grams. Okay, so these are some of the numbers over there. Okay, you guys don't have to memorize those numbers. They should be given, or you can look it up when you are doing your homework. Okay. All right. So we'll take a look on one of the conceptual questions, or maybe a couple of them here, on the law of inertia. Okay, so unless there's a force on the object, then it's either keeping its original velocity or staying at rest. Okay, so let's take a look here. So when you are driving down the road, you hit the brake suddenly. Maybe you are seeing something on the road or whatever. But as a result, your body moves towards the front of the car. Okay, so try to see if you can explain this using the Newton's law of inertia. All right, I'll give you guys a few seconds to think about how you want to explain this, and then I will explain it, and then to see if your explanation matches with mine. All right. So when you are driving, right? So your body and the car has a certain speed, right? It's going in that way, right? Or yeah, going in one direction. Let's say going in one direction. When you hit the brake, right? Your car comes to or slows down quickly, but your body still maintains its original velocity, right? So then it's actually the car slows down, but your body keeps going forward with the same direction. Okay, so that's how the body and the car kind of separated. Okay, little bit. So that's why you feel your body is moving forward. Actually, your body just keeps moving. Okay, it's the car that slows down. Okay, so you feel that your body is leaning forward. Okay, so for your body, then it keeps its original velocity. Okay, so that's the law of inertia or Newton's first law on your body. Okay. The second one here, is it possible for an object at rest to have only one single force acting on it? If your answer is yes, provide an example. If your answer is no, explain why. Okay. So think about if it's possible for an object to have only one single force acting on it and remain at rest. You can submit your answers by clicking on the question here. It's okay that you don't have an example. Okay, you can just say yes or no for right now. That if you can have an example, that would be better. All right. So I see a lot of you guys says yes. For example, gravity is the only force acting on your body. All right. Think about that. So let's go back to the example here. Okay, when we have a book resting on your hand or resting on the table or on the ground. Okay, so actually it's not a single force of gravity, right? The weight is the force of gravity, but there's a supporting force because when we are standing here, the ground is supporting us, and then the earth is pulling us down. Okay, so there are two forces here. Okay, they balance out. Okay, so that's what happens. Okay, so when you think about if an object is resting, so there must be forces balanced out. Okay, so it's not a single force acting on the object anyway. Okay, so there should be more than two. If there's one single force, okay, so let's think about For an example, like the Earth, in the solar system, the Earth is being pulled by the sun due to gravity of the sun on the Earth, right? So it's a single force in that scenario. We can ignore all the other gravitational forces from the other planets. Compared to the sun's gravitational force, those are negligible, okay? So you can see in that scenario, then the Earth is actually moving around, orbiting, right? It's not staying at rest, okay? So if you just have one single force and up and in the up on the object, then the object will start to move. Okay, we will not stay at rest because then it's being pushed, either pushed or pulled. Okay, so it will not. So the answer for this one would be no. Okay, if there's just one single force on the object, then that means there's net force on the object. So according to Newton's second law, if you have force, so the first law says unless compelled by a net force, the object will remain at its initial state of either at rest or moving, right? So then the counter statement should be if there's a external force on the object, then the object will change its status. Okay, so if it's at rest, it will start to move. If it's moving, then the velocity will be changing. Okay, so the answer should be no. Okay, because then you will have net force on the object, then it will start to move. All right, we'll take a look on another one here. Which of the following statements are correct? Okay, so you might have more than one correct statement here. Okay, I see your responses there. So let's take a look these statements one by one here. Okay, so the first one here says a net force is required to keep an object moving with constant velocity. Okay, so some of you guys says this is correct, but it's actually false, a false statement, right? Because if there's a net force, then the object's velocity will be changing. Okay. First law says unless there's a net force, the velocity will not be changing. So then if there's a force, then the velocity will be changing, right? So if there's a net force, then you'll have changing velocity, right? Or to give you an example, say if something, or if you say if you have a skateboard, if you give it a push, right? So after you release it, it's going to continue moving, right? You don't need to add any force to it, right? So it keeps the velocity of itself when it's rolling away, but you don't need a net force on it, okay? So this one is false, okay? If you have a net force, then velocity will be changing. You cannot keep the constant velocity in that scenario. B says a net force is required to make an object oscillate, okay? So the first law, when it says unless there's net force, the velocity will not be changing. And then, so the other way of saying this is if there's a net force, then the velocity will be changing, right? So if you have changing velocity, then what would be the cause? That's because there's oscillation, right? Because if you have change in velocity, then that means there's oscillation. According to definition of oscillation, oscillation equal to change in velocity divided by time t, right? So if there's a change in velocity, then you will have oscillation. Okay, so B is correct. C says when you hit the brakes in the car, a force pushes you forward or towards the front of the car. Okay, so I think C and D, they are your perceptions, right? Because in order for a force to push on you, then there's something has to exert that force on you, right? There's nobody pushing you, right, in that scenario, right? Nothing is pushing on you in that scenario, right? It's just your perception that because your body is keep with its original velocity going forward, but the car slows down. So then your body kind of lean forward. You feel you are being pushed forward, but actually there's nobody or nothing pushing on you. So there's no real force on you, okay? Just because you are keeping your original velocity, but the car slows down in that scenario, all right? So that's just a perception. This is not correct, okay? Physically, there's nobody or nothing pushing on you. Similarly, on D here, when you oscillate your car, a force push you back into your seat, okay? So nobody is pushing you from in front of you, right? Or nothing is pushing you. It's just because when the car is oscillating, its velocity start to increase, but your body has a tendency of keeping its original velocity, a slower velocity, okay? So then you feel that way someone is pushing you back into the car, but it's actually not that case, okay? So C and D, they are both false. It's just our perception. On D here, it says an object that is moving will continue to move with the same velocity unless a net force acts on it, okay? So this is exactly Newton's first law statement, okay? So then this one is correct, okay? It will continue with the same velocity if there's no net force, okay? If there's no net force, then you'll keep its original velocity, either at rest or with a certain velocity, okay? So the correct statements are B and E, okay? B and E on this one. The rest are not correct. All right. So yeah, I think we are going to stop over here for today. And then we'll check on the second law next time, okay? There's a message here. Oh, sorry to hear that.